Welcome to the bilingual e-lecture session for diploma students. Today we are going to see the stress strain diagram and the problems related to the mechanical properties of materials in this session. This portion is coming under Unit 2 of Strength of Material subject for secondary mechanical engineering students. Now let us go to the topic. Tensile test on mild steel in the universal testing machine. UTM is usually called as universal testing machine. UTM is the acronym for universal testing machine. All engineering materials do not show same sort of behavior when subjected to tension as well as compression. மெட்டீரியலோட ப்ராப்பர்ட்டியை பொறுத்து அதோட பிஹேவியர் இருக்கும். கம்ப்ரெஷனில் இருக்கும், டென்ஷனில் வித்தியாசமாக இருக்கும். இட் பியூர்லி டிபெண்ட்ஸ் அப்பான் த ப்ராப்பர்ட்டி ஆஃப் த மெட்டீரியல்ஸ். போன செஷன்லேயே நம்ம பார்த்தோம் வாட் ஆர் த மெக்கானிக்கல் ப்ராப்பர்ட்டிஸ் ஆஃப் மெட்டீரியல்ஸ். சம் மெட்டீரியல்ஸ் மே பி குட் இன் சம் மெக்கானிக்கல் ப்ராப்பர்ட்டிஸ் such as malleability, castability, weldability, like that. Some materials will be very strong in stiffness, toughness, like that. There exist some materials like metals, alloys, which are more or less equally strong in both tension and compression. நம்ம பார்க்குறது வந்து tension and compression மட்டும் பார்த்துட்டு இருக்கோம். இப்போ இந்த tension and compressionல some materials like metals and alloys அது tensile forceக்கும் என்ன பிஹேவியர் காமிக்குதோ அதே அளவுக்கு ஈக்குவலாக கம்ப்ரெஷனுக்கும் காமிக்குது. These are all good materials to be used in the manufacturing of components, and these materials are generally tested for tension only. Okay, these materials are generally tested for tension because they exhibit similar properties or similar behaviors when they are subjected to compression also. என்கிட்ட டென்ஷனில் என்ன டெஸ்ட் பண்ணும் பொழுது அது எப்படி பிஹேவ் பண்ணுதோ அதே பிஹேவியர் தான் கம்ப்ரெஷனில் இருக்கும் அப்படின்றத அசியூம் பண்ணிவிட்டு we are allowing the materials to be tested in tension. Some materials like concrete, stones, bricks are weaker in tension but stronger in compression. இப்போ காங்க்ரீட் எடுத்துக்கிட்டிங்கன்னா காங்க்ரீட், ஸ்டோன்ஸ், பிரிக்ஸ் இந்த மாதிரி மெட்டீரியல்ஸை எடுத்துட்டிங்கன்னா அது டென்ஷனில் வீக்காக இருக்கும். பட் எப்படி இருக்கும் அப்படின்னா கம்ப்ரெஷனில் ரொம்ப ஸ்ட்ராங்காக இருக்கும். ஸோ இந்த மெட்டீரியல்ஸ் என்ன பண்ணணும் அப்படின்னா we have to test them in compression only. So it is a small stress strain diagram drawn for a material. In the x-axis we are having the strain values and in the y-axis we are having the stress values. You can see the diagram. It starts from O, from O to A. It is like a straight line, then there is a small curve from A to B, then there is a bending from B to C, then once again there is a step down curve from C to D, then from D to E another curve, then E to F. We will see them one by one. First, what is point A? Point A on the stress strain curve is a point up to which the plot is a straight line. Plot in the plot it is a straight line. Here the stress is directly proportional to the strain. Here the stress is directly proportional to the strain. So up to point A stress is directly proportional to strain. Up to proportional limit, up to this limit, proportional limit, the material remains elastic and strictly follows the Hooke's law. Okay, it remains elastic. This is the elastic stage up to which the material remains in the elastic stage and it obeys the Hooke's law Then point B. What about B? It is the point just beyond the proportional limit. From the proportional limit to elastic limit, the material remains elastic but does not follow Hooke's law, and so stress and strain are not proportional. Up to A, stress is directly proportional to strain and it obeys the Hooke's law. It obeys the Hooke's law. Okay, but from A to B there is some variation. It is like a curve. In this curve, okay, the material remains elastic. Up to this point, material is in elastic stage but does not follow the Hooke's law. Here it will not obey the Hooke's law in this portion. Okay. Then comes point C. Point C represents upper yield point. Point C represents upper yield point and point D represents lower yield point. The stress at which there is a sudden increase in strain without any appreciable increase in stress is known as yielding. Yielding na enna? Sudden increase in strain. Strain value increase ஆகுது. Strain value increase ஆகுது without that much increase in the stress value. நம்ம என்ன படிச்சிருக்கோம்? Stress is directly proportional to strain. So stress value increase ஆனா strain value increase ஆகும். Stress value decrease ஆச்சுனா strain value என்ன ஆகும்? நமக்கு decrease ஆகும். But at a point ஒரு குறிப்பிட்ட நேரத்தில் என்ன ஆகும் அப்படின்னா stress value வந்து strain value will increase without any appreciable increase in the stress. Stress அவ்வளோ அதிகமாக இன்க்ரீஸ் பண்ணலைன்னா கூட என்ன ஆகும்? நமக்கு வந்து strain value வந்து இன்க்ரீஸ் ஆகும். அந்த பாயிண்ட்டை என்ன சொல்கிறோம் அப்படின்னா yielding அப்படின்னு சொல்கிறோம். The point from which yielding starts is called as yield point. In the chart, C represents upper yield point and D represents the lower yield point. Then comes the point E. What is point E? After yielding, the material attains the maximum load at E, beyond which the load falls with elongation increasing at a rapid rate. The stress corresponding to point E is known as ultimate stress. The stress corresponding to point E is known as ultimate stress. As the load falls from its maximum value, a sudden yielding of the bar takes place over a short length forming a neck. So we are having a rod like this. Okay, it is a ductile material. Rod is made of ductile material. It is subjected to tension. At point E, the rod tends to form a neck. At this stage, at the point E. We have already discussed what is tensile force in an object if there are two axial pulls, then the object is said to be under tension. Due to the applied tensile force, the length of the object will increase and the diameter of the object will decrease. Length will increase and the diameter will decrease. Diameter of the object will decrease. So there is a formation of neck in the testing rod. Then what about point F? Point F represents the breaking point. At this stage, the elongation increases at rapid rate and the area of cross section of the bar occurs fast reduction. The specimen breaks at the point F. So we are having a specimen. It is nothing but a rod A, B, C, D, E up to E. It remains as it is, and from E it starts to form a neck. Okay, it starts to form a neck, and at point F it fails, and there is a drastic reduction in the diameter of the rod. It is nothing but the cross section. The specimen breaks at the point F. The stress corresponding to the breaking point is known as breaking stress. It is called as breaking stress. The value of breaking stress will be less than the ultimate stress. Now we can determine the percentage of elongation. Percentage of elongation is given by LO minus L divided by L. LO minus L divided by L. So, we are having a rod of length L. This is the original length. It is subjected to tensile force. Because of the tensile force, okay, after reaching the point E, there is a reduction in the cross section. There is a reduction in the cross section of the rod. So, there is a change in the rod. There is a change in the rod. Increase in the length of the rod, it is given by del L. So, we can determine the original length of the rod after fracture as LO. So, LO is going to be the length of the testing specimen or rod after fracture, and L is going to be the original length. From this we can determine the percentage of elongation. Similarly, the percentage of area reduction can be determined by the formula d square minus d square by d square into 100. What is capital D? Capital D is the original diameter. Capital D is the original diameter. Now, this diameter is reduced to a smaller value. So, small d is the diameter of the rod at the neck. So, using these values, we can determine the percentage of elongation and the percentage of area reduction of the bar subjected to tensile load. Now, we will look on to a problem. A specimen made of steel having 25 mm in diameter with a gauge length of 200 mm was tested in a laboratory. Okay. So, 25 mm diameter steel rod, okay, length is 200 mm. It was tested in a laboratory. The following data were referred. Maximum load is 140 kilonewton. Load at yield point is 110 kilonewton. Load at fracture is 120 kilonewton. Diameter of the neck is 12.5 mm. Distance between the gauge marks after fracture is 252 mm. So, using this value, we got to find yield stress, ultimate stress, nominal stress at fracture, percentage of elongation, percentage of reduction in area. Now, we will go to the problem. What are the given data? Original diameter D is 25 mm, original length, that is nothing but the gauge length 200 mm, maximum load 140 kilonewton, this is going to be 140 Newton, 40,000 Newton. Load at yield point Py is given by 110 kilonewton, it can be converted into Newton. Load at fracture is 120 kilonewton, it can also be converted into Newton. Neck diameter, it is also given 12.5 mm. Then length after fracture is given as 252 mm. Length after fracture is given as 252 mm. Since it is subjected to tensile, you can see original length is 200. Now it is increased to 252 mm. Now we are going to find the value of yield stress, ultimate stress, nominal stress at fracture, percentage of elongation, percentage of reduction in area. We will see them one by one. So, what is the original area? Original area A is equal to pi by 4 d square. We know the value of d, original diameter of the rod. What is capital D? Original diameter of the rod or the diameter of the rod before the testing process. So, it is going to be 490.87 mm square. Then yield stress, what is the formula for yield stress? Yield load divided by area resisting the yield load. It is also given, okay, we can directly calculate 224.09 Newton per mm square. Then second step, we go to find the ultimate stress. What is stress? Stress is equal to load by area. Ultimate stress is equal to ultimate load by area. It is also given, we can calculate the value of ultimate stress. Then normal stress or nominal stress at the fracture, it is given by load at the fracture divided by area. So, we can substitute the values and we can find the values very easily simply by means of simple substitution, and using the calculator we can calculate the value. What is the percentage of elongation? Percentage of elongation is given by the formula LO minus L by L, where L is the length of the original object and LO is the length of the object after fracture. So, 252 minus 200 by 200 into 100%, that is going to be 26%. Percentage of reduction in area. percentage of reduction is given by d square minus d square by d square. What is capital D? Original diameter of the rod. What is small d? Original diameter of the rod is reduced in the neck. The neck diameter is small d. So it is given by 25 square minus 12.5 square divided by 25 square. So it is going to be 75%. It is going to be 75%. Now we can summarize the results. Yield stress, ultimate stress, nominal stress. They are having the units Newton per mm square. Don't forget to put the units. Okay. Then percentage of elongation and the percentage of reduction in area. Percentage of elongation in length. Okay. Elongation itself means length. 26%. Reduction in area is 75%. Okay. Is it clear? Okay. Now we are going to find out the formulas used to determine the volumetric strain on rectangular and circular bars. For determining the linear strain, we got to use the formula change in length to original length. To determine the lateral strain, okay, we can use change in diameter to original diameter, change in width to original width, change in thickness to original thickness, since it is going to be lateral strain. Volumetric strain, what is the formula for volumetric strain? Change in volume to original volume, or it can be given by the formula E into 1 minus 2 into 1 by m. We know E and we know 1 by m. Poisson ratio is given by 1 by m is equal to lateral strain to linear strain, and Young's modulus is given by stress by linear or longitudinal strain, and the bulk modulus is given by stress by volumetric strain. Using these formulas, we are going to solve the problems. For the rectangular bar, what is the area? Okay, it is a rectangular bar. Okay, it is a rectangular bar. So what is the area? For lateral strain, it is going to be width into thickness. Okay, B into thickness. Volume, length into breadth into thickness. For cylindrical component, it is going to be d, pi by 4 d square, pi by 4 d square into L, where L is going to be the length of the cylindrical rod. Okay. All values are in mm. The final dimensions can be adjusted like this. Okay. For the rectangular bar subjected to axial load, tensile load, final length is going to be L is equal to, final length is equal to original length plus change in length. Width is equal to original width minus change in width. Thickness, final thickness equal to original thickness minus change in thickness, because it is subjected to tensile load. In the tensile load, length will increase, other dimensions will decrease. If you are going to consider the compressive load, then what will happen? Length is going to reduce, other dimensions will increase. So the final length will be initial length minus change in length. Final width B is going to be initial width plus change in width. Okay. Final thickness is going to be initial thickness plus change in thickness. Okay. You imagine an object. Now we are going to apply the compressive force. Because of the applied compressive force, length will shrink. Okay. Length will reduce, but width and thickness will increase. But if the object is subjected to tensile force, what will happen? Length will increase, other dimensions will decrease. Okay. This is the concept. For cylindrical component, length is going to be initial length plus change in length. Final diameter is going to be initial diameter minus change in diameter. But the same cylindrical rod, when subjected to compressive load, what will happen? Length is going to be L minus del L. Length is reduced, diameter is increased, d plus del T. Now we will try to solve a problem using the formulas we learned just now. A bar of 30 mm cross 30 mm cross 250 mm long is subjected to a pull of 90 kilonewton in the direction of its length. The extension of bar was found to be 0.125 mm, while the decrease in each lateral dimension is found to be 0.00375 mm. Find the Young's modulus Poisson's ratio, modulus of rigidity and bulk modulus for the material of the bar. So, the size of the bar is given, width and thickness, length. It is subjected to an axial pull. What is meant by pull? It is a tensile load. 90 kilonewton in the direction of its length. So, it is axial load. Extension of bar was found to be 0.125 mm. It is nothing but del L. Increase in the length, decrease in each lateral dimensions are found to be 0.00375. It is nothing but del W and del T. This is going to be del L. Because of the applied load, since it is a square rod applied to subjected to tensile load, subjected to tensile load, length will increase, breadth and thickness will decrease. What we got to find? We got to find the Young's modulus, Poisson ratio, modulus of rigidity and the bulk modulus for the material. So, the given data, width, thickness, length, load, it is given in kilonewton. So, we have to convert them into Newton, change in length, change in width and thickness to find Young's modulus, Poisson's ratio, modulus of rigidity and bulk modulus Look at the problem. So, how to find the lateral strain? Lateral strain is given by change in width to original width or change in thickness to original thickness. So, lateral strain is given by 1.25 into 10 to the power minus 4 simply by direct substitution of values, that is all. What is linear strain? Linear strain is given by del L by L. Here also we are going to directly substitute the values and the linear strain is going to be 5 into 10 to the power minus 4. Then we are going to determine the Poisson's ratio. What is Poisson ratio? Poisson ratio 1 by m. It is given by the formula lateral strain by linear strain. It is given by the formula lateral strain by linear strain. Both are given. We go just now we have calculated the value, substitute this value for lateral strain and linear strain. We will get the value of Poisson's ratio as 1 by m is equal to 0.25. Since it is a ratio, it has no unit. Then Young's modulus. To determine Young's modulus, we need the area. Area is going to be B into T. It is going to be 30 into 30, 900 mm square. Young's modulus E is given by PL by A into del L. E is equal to PL by A into del L. We know the value of P, load. We know the original length L. We know the area A, just now we have calculated as 900 mm square and the change in length is given by 0.125 mm. We can easily calculate the value of Young's modulus using a calculator. E is equal to 2.2 into 10 to the power 5 Newton per mm square, 2 into 10 to the power 5 Newton per mm square. Then we are going to find the value of modulus of rigidity. What is the, how to find the value of modulus of rigidity? Modulus of rigidity n is given by a relationship between Poisson ratio and Young's modulus. Young's modulus E is equal to 2 into n into 1 plus 1 by m, where 1 by m is the Poisson ratio and E is the Young's modulus. 1 by m just now we have calculated as 0.25, E is 2 into 10 to the power 5, it is given. So, we can calculate the value of n as 0.8 into 10 to the power 5 Newton per mm square. Similarly, we can calculate the value for bulk modulus. How to calculate the value for bulk modulus? Bulk modulus K is given by a relationship between the constants as Young's modulus E is equal to 3 into K into 1 minus 2 into 1 by m, where 1 by m is the Poisson ratio. Just now we have calculated, it is nothing but 0.25. So, by substituting the value of Young's modulus as 2 into 10 to the power 5, we can calculate the value of K as 1.3 into 10 to the power 5 Newton per mm square. So we can summarize the results as Young's modulus E is equal to 2 into 10 to the power 5 Newton per mm square, Poisson ratio 1 by m is equal to 0.25, modulus of rigidity is 0.8 into 10 to the power 5 Newton per mm square, bulk modulus K is equal to 1.3 into 10 to the power 5 Newton per mm square. Okay, we have calculated Poisson ratio, Young's modulus, then modulus of rigidity and the bulk modulus. Okay. So with this we are coming to the end of the problem. Now we have to summarize this one. Now we are moving on to the next topic, composite bars. Okay. If we have two materials, material 1 and material 2, how to calculate the load, stress and the change in the length. Okay. Load is given by P E1 A1 divided by E1 A1 plus E2 A2, and for material 2 it is given by P E2 A2 divided by E1 A1 plus E2 A2. Okay. A is nothing but area of cross section of the first material, A2 is the area of cross section of the second material, E1 is the Young's modulus for the first material, E2 is the Young's modulus for the second material. Similarly, stress can be calculated, it is sigma 1, here it is sigma 2, change in length can be also calculated by using these formulas. Okay. In composite material, strain is equal for both the materials. We have already discussed this one in the previous sessions. Okay. In the composite material, all the materials behave as same in strain. Okay. So the strain is equal for all the materials. So we can compare strains of first material with strain of first material with strain of second material. What is strain? Strain is equal to stress by Young's modulus. Strain is nothing but strain is given by the formula stress by Young's modulus. Okay, what is Young's modulus? Young's modulus is the ratio of stress to strain. So from this we can calculate the value of strain as ratio of stress to Young's modulus. So we can equate the two strains E1 and E2, we will get sigma 1 by E1 is equal to sigma 2 by E2. Okay, where sigma is the stress and E is the Young's modulus for the specific material. By using this formula, we can do lot of calculations. Next one is temperature stress. Temperature stress is equal to temperature strain into Young's modulus. Temperature strain into Young's modulus. Similarly, temperature stress is given by the formula load by area. Okay, load by area, stress is equal to load by area. By using these two equations, we can do lot of calculations. We can find out what is required. Okay, what are the unknown values? Condition 1, free expansion prevented. It is nothing but supports do not yield. Supports do not yield. No allowances for expansion. No allowances for expansions. For these conditions, the temperature stress is given by the formula alpha into T into E. It is given by the formula alpha into T into E, where alpha is the coefficient of expansion, T is the rise or fall in temperature, and E is the Young's modulus, and E is the Young's modulus. E is the Young's modulus. Condition 2, supports yield. Allowances for expansion as del is equal to x mm. So it is given by the formula temperature stress is equal to alpha T1 minus alpha into T1 minus change in length. So we are going to have allowance of x mm, del is equal to x mm divided by L into E. The unit is going to be Newton per mm square. Condition 2, supports yield or allowance of expansion is given as in terms of percentage. Here the temperature stress is given by 100 minus x by 100 into Te Newton per mm square into Te Newton per mm square. So with this we are coming to the end of this session. In this session we solved some problems and we have learned how to find out the values for temperature stresses and how to solve the problems related to composite bar. Okay. Thank you. We will meet in the next session. Thank you.